Okay, we want to look at some more examples involving Newton's laws, specifically Newton's second law. Okay, here's an example. I've got a sign that's been hung from the ceiling, and you can see I've indicated the ropes going from the sign to the ceiling, and there's going to be a tension in one rope, which I've labeled as T1, and a tension in the other rope, which I've labeled as T2. These ropes are at different angles, theta 1 and theta 2, and of course the weight of the sign is pulling it down. And so the problem says a 7.5 kilogram sign is haphazardly hanging from the ceiling as shown. The angles are theta 1, that's this one, is 60 degrees, theta 2, that's this one, is 30 degrees, and the question is, what is the tension in each rope? Okay, so we want to find the tension in each rope. How are we going to approach this problem? Well, we have drawn our picture and we have set up our coordinate system. We have the x-axis and the y-axis showing us directions. We've labeled our force factors. We've got the tension in rope 2, the tension in rope 1, and the weight mg pointing down. And what we want to do is break all the forces into x and y components, and then we'll apply the rule that the sum of the forces in the x direction is the mass times the acceleration in the x direction, and the sum of the forces in the y direction is the mass times the acceleration in the y direction. What does that mean? So I want to break these guys up. So this T2, for example, I can break it up into an x component, and that would maybe be called T2x, and I can break it up into a y component, and I would call that T2y. Now notice both the vectors T2x and T2y, these are the x and y components of T2, they're both pointing in positive directions. Now if I wanted to do the vector for T1, I can do the same thing. I can say that T1 is going to have an x component like this, and that would be T1x, and it's going to have a y component like that, and that would be T1y. Now notice T1y is positive, but T1x is in the negative direction. And so what I've done is I've put my force vectors on my picture for all the forces. I've broken them all into x and y components. The weight is obviously all in the y component already. I didn't have to do anything to that. But both of these tensions were at angles, so I had to break them into x parts and y parts. So now what I want to do is the sum of the forces in the x direction and the sum of the forces in the y direction. So again, I have my T2x, which is pointing like this, and I have my T1x, the x component, which is pointing like that, and those are the only forces acting in the x direction. So I can do my sum of the forces in the x direction right here. There's going to be the positive T2x, this one is positive, it's pointing in the positive direction, minus T1x, and those are the two forces acting in the x direction. And so when I do a little algebra, I find that T2x and T1x are equal to each other. Now, I can note that if I think about this triangle here and that triangle there, T1x is simply T1 cosine of theta, and T2x is simply T2 cosine of theta, theta 1 and theta 2 respectively. And so now I want to do the sum of the forces in the y direction. And remember, I'm going to have a y component here. This is going to be my T2y. And I'll have a y component there. That's my T1y. And so I can see that both of these tensions have y components that are pointing upward, and of course the weight, or the force of gravity, is pointing downward. And so when I do the sum of the forces in the y direction, I get the positive T2y plus the positive T1y minus mg equals to 0. Now T2y, that's going to be T2 times the sine of theta 2. T1y is T1 times the sine of theta 1. So I can plug those in. So T2y is the T2 times the sine of theta 2. T1y is T1 times the sine of theta 1 minus mg equals to 0. I can plug in the values and I get that 0.5 T2 plus 0.866 T1 is equal to 73.6 newtons. That's m times g. But on the previous slide, I saw the relationship that T2 is equal to 0.577 T1. So what I can do is take this T2 and plug it into there. And so I'll get 0.5 times 0.577 T1 plus 0.866 T1. And when I multiply that out and add everything together, I get 1.15 T1 is equal to 73.6 newtons. Solving for T1, divide both sides by 1.115, and that gives me T1 is 64 newtons. Now T2, we already said is 0.577 T1, so I can plug in 64 newtons, and I get the value for T2, and now I have both the tensions, T1 and T2, the problem is solved. Okay, now this is a famous physics problem, and it has lots of different variations, and you're going to get to see some examples of this in other configurations, but the basic idea is you have two masses that are unequal, strung over a pulley, and they're allowed to just slide up or down the pulley. Now, here we're going to work an example, and I've got some actual numbers for you. I've got M2 is the bigger mass, and it's got a mass of 0.6 kilograms. M1 is a smaller mass. It's got a mass of 0.4 kilograms, and these are strung over by an ideal cord. We know what that means. It doesn't stretch, and its mass can be ignored, and it's strung over what we call an ideal pulley. And so I'm going to go down to Diagon Alley and get me an ideal pulley. That's one that also has a mass that can be ignored and has no friction. So the friction and the mass of the pulley are negligible, and we're just going to consider the forces acting on these masses. Now the problem is to determine the tension in the cord and to determine the acceleration of these two masses. Now since it's an ideal rope, we know the rope can't stretch, and so the motion is they're going to have the same acceleration. What's different though is that this one's going up and this one's going down. And there's a weird way that you have to think about that to understand how to set this problem up. Now, just as an aside, why is this called the Atwood's machine? Because this was a machine that was developed by a guy named George Atwood, and this was done back in the 1700s, and it was used to systematically study acceleration or motion with constant acceleration. And so one of the things that it is really useful for, it was back in the 1700s, they didn't have fancy stopwatches like we had today, and so he was able to use this contraption to slow down the accelerations and make very accurate measurements of how things accelerated with different forces, and particularly he was able to measure the acceleration due to gravity to very high precision. And you know, you can see this picture, it's a little bit more complicated than the one that I put in the previous slide, but these were complications designed to deal with factors like he could compensate for friction and things like that, which we're pretending don't exist. But the basic idea of the Atwood's machine, that's what we want to explore. Now here's the weird thing that you have to think about. Block 1 is going to go up, block 2 is going to go down, but they're really going in the same direction. They have to go in the same direction because the rope is not allowed to stretch. And that's kind of weird to say. What does that mean, they're going in the same direction? Well, think of it like this. If this were not on a pulley but just on a flat surface, and I'm pulling these two blocks to the right, if block 2 goes to the right 5 meters, block 1 goes to the right 5 meters. Now, rather than saying to the right, let's say in the positive direction. If block 2 goes in the positive direction for 5 meters, block 1 has to go in the positive direction for 5 meters. And so if block 2 on the pulley goes downwards for 5 meters, block 1 going upward for 5 meters, that means they have to be going in the same direction, so the directions reverse on either side of the pulley. That's so weird, isn't that weird? Well, actually, it makes perfect sense if you think about it in the right way. So forget the math over here for a second. Let's look at the pulley. what I've done is I've added my coordinate system, and imagine my coordinate system is glued to the string. And so as mass 1 goes upwards, my x is going upwards, my coordinate system is going upwards. But when they go over the pulley, my x is now pointing upside down. So the coordinate system indeed reverses on opposite sides of the pulley. And so on the left side of the pulley, going up is a positive, but on the right side of the pulley, going down is a positive. And that's important because these coordinate systems, they tell us what are positive and negative forces when we do the sum of the forces. Now let's do it. I've got two masses here, M1 and M2. I've got the tension in the rope pulling up. I've got the weight pulling down. I've got M1 and M2, so I'm very careful with my labels. It's not MG, it's M1G. Here, it's M2G. Now the tensions are going to be the same. That's basically just a Newton's third law kind of a situation. And so I can isolate the forces on each block. So let's consider block number 1. So this is block number 1. There's two forces. They're both in the x direction. I've defined this as my x direction. So normally we would call that y, but today I feel like calling it x, so that's what I'm going to call it. This is my x direction, and the forces are a positive t, because it's going in the same direction, and a negative weight, m1g. Over on the right side, I've got, this is my coordinate system now, so if I'm looking at block 2, I have a negative tension, because this is now pointing in the negative direction, and a positive m2g. And so the signs reverse because this coordinate system is flipped over. So now I'll just isolate my two blocks and do it. For M1, the sum of the forces is, again, we have a positive t minus m1g, t minus m1g, and that's equal to the mass times acceleration. What mass is being accelerated here? M1. So that's M1a. For block 2, we have the sum of the forces is m2g. Now that one's now positive, and then the t is minus, and so I have m2g minus t, and that's equal to m2a, because it's m2 that's being accelerated. Now, what do we have here? We've got an equation that has multiple unknowns. We don't know the tension, we don't know the acceleration. We don't know the tension, we don't know the acceleration. But we also have two equations. Two equations, two unknowns. So I could solve this one for the tension and then plug it into there. And that's the usual way that you solve a system of two equations that have two unknowns. But if I look, instead, I've got this positive tension here, this negative tension there. If I simply add these two equations together, the tensions will cancel. And so if I add them together, I get t minus, on the left-hand side, I would get t minus m1g plus m2g minus t. The t's would cancel. I'd have t minus t, and I'd end up with, on the left-hand side, m2g minus m1g. On the right-hand side, I'd end up with m1a plus m2a. And so that's what I have here. m2g minus m1g equals m2a plus m1a. Factor out the g on the left side, factor out the a on the right side, solve for a, and I get m2 minus m1 divided by m2 plus m1 all times g. So now I can plug in my values for my masses, multiply it by little g, and I end up with an acceleration of 1.96 meters per second squared. Now the problem said also find t, so what can I do? I can take this acceleration, plug it into here, and solve for t. Now before I do that, I want to point something out here. This expression for the acceleration, I mentioned that Atwood's machine was used to measure the acceleration due to gravity. Now if I just drop a ball to the floor, it's going to hit the floor really quickly. It's hard to measure that very accurately, especially in the 1700s, because that motion is very, very quick, and they didn't have very good clocks back then. But if instead I hang these masses, let's say these masses are close. So let's say this is 500 grams and 510 grams. That's not the values in our problem, but let's just say they were. This difference would be 10 grams, and this sum would be about a kilogram, a little bit more than a kilogram. So I would have a very tiny number divided by a very big number, and my acceleration would be very small. It would be a fraction of little g. But if I could measure my masses very accurately, I could measure the acceleration, which is now very low. I could measure it very precisely, and then I could plug in the masses and calculate what g would be. So that's how Atwood actually was able to use his experiment to measure the value for little g. Now, what we want to do is actually find the tension. And so we're going to plug in our values for M1G, our value for M1 here, and our value for A. And so here I've got my tension, it's minus M1G. Now, if I wanted to, I could plug the numbers directly in, but I just want to show you the relationships before we plug in numbers. If I were actually working this problem, I'd go ahead and plug in numbers. But if we solve for t, we find that it's M1G plus M1A, and we can factor it out, the M1, and that gives us M1G plus A. And so you can see that's a very simple relationship. Now I'm going to plug in the numbers now, and when I do, I get my tension works out to be 4.71 newtons. Okay, here we have an example involving what's called an inclined plane. Now the example says a mass m slides down a smooth, that means there's no friction, inclined plane that makes an angle theta with respect to the horizontal. So here we have the horizontal, which is left to right, and there's a plank or something that is elevated at an angle theta, and then we have a box that can either slide up or down the incline. So you could elevate a plank, you could have a hill, any sort of flat inclined surface. This is what we're talking about. And this box is going to just slide down. Now, the question asks, what is the acceleration down the plane, and what is the normal force exerted on the mass by the plane? Now, anytime you have an inclined plane problem where the object is sliding up or down the plane, you'll want to tilt your coordinate system so that the coordinate system points down the plane or up the plane and is also perpendicular to the plane. So here I've got this box here is going to slide down the plane. I've got my coordinate system tilted so that the x-axis lines up with the motion of the box, and the y-coordinate is perpendicular to the motion of the box. And so the reason that we do that is if I have a normal coordinate system, one that looks like this, as this box slides down the inclined plane, it would be moving in both the x and y directions. But by having my coordinate system tilted over here, all of the motion lines up with the x-axis, and so we have a much simpler mathematical problem to deal with. It's effectively motion in a straight line. And so there will be no motion in the y direction, and that makes it a lot simpler for us to tackle the problem. Now, here you can see my coordinate system that I've picked is pointing down the plane, and that's the one that I would choose if the block were sliding down the plane. That way, all my motion is in the positive x direction. However, if I had a box that was sliding up the plane, maybe you gave it a good shove and it's sliding up the plane, I would make my coordinate system line up like that. So I just like to have my motion be in the positive direction when I can. And of course, the box could go up the plane, come to rest, and then slide down the plane, and either of the coordinate systems would be fine for that. You just have to pay attention to which values were in the positive direction and which values were in the negative direction, and that would depend on which of those two coordinate systems you picked. Now, when you have an inclined plane, one of the things that's tricky to see, but that it's important that you understand, is the relationship of the angles. And so here I have a visual representation of two boards that are connected together by some kind of hinge, and I've glued an XY coordinate system onto the edge of the topmost board. And now I'm going to open it up, raise the top board up at some angle, and so I've taken the boards and I've moved the top board up at some angle theta. And what I want you to see is my coordinate system, which was originally in the normal orientation, it's going to tilt up. And so my blue original coordinate system is going to tilt up. So if this board moves up an angle theta, the x-axis is going to increase that same angle theta. And so this would become my new x-axis. And of course, my y-axis is going to tilt down the angle theta, and this would become the direction of my new y-axis. But what I really want you to see is that as the inclined plane is lifted up some angle theta, the x and y axes both have to tilt over that same angle theta. And by the way, that's going to be true. We can extend this axis like this, the x-axis like that. So the x-axis would have to tilt down here, and this axis would have to tilt over there. So all of these axes are going to move the same angle theta. Now, as we said previously, if a block is sliding up or down the incline, the best coordinate system to use is one that is parallel and perpendicular to the plane. In this case, all the motion along the plane is going to be in one dimension. So, let's look at this green coordinate system here. This would be maybe a possible x and y coordinate system in a problem. So, this would be my x-axis and this would be my y-axis. And we know that the y-axes will have been tilted over by some angle theta. And that's going to be important for us when we analyze the angles that are at play with the inclined plane. Now let's go back to our example. We have a block and it's sliding down an inclined plane. Now I have defined a coordinate system right here, and I chose x to be positive going down the inclined plane and y is perpendicular to the inclined plane. And I've got my box here, and I've drawn the two forces on it. Now we said in the problem there's no friction to worry about, so there are only going to be two forces acting on this inclined plane. There's going to be the normal force, which remember is always perpendicular to the surface. So the inclined plane this is the surface. The normal force has to be perpendicular to the inclined plane. That means it's going to line up with the y-axis. So that's one of the reasons that you get a benefit from orienting your coordinate system that way. Your normal force is going to be lined up. Now, unfortunately, your weight, m times little g, it does not line up with the y-axis anymore. But from what we've seen previously, I think it'll be clear to you that it does make an angle that is familiar, because I've drawn in. Now remember, this mg is going to be pointing straight down, but it's going to be making this angle with our tilted coordinate system. So the normal coordinate system that we might do like that, this line here would line up with mg. But when the coordinate system gets tilted over and everything goes up an angle and that goes up an angle, that means that whatever angle the inclined plane is tilted over, that means that this axis is also going to be tilted over the same angle theta. And so that's the key thing to understanding the geometry of this picture. Now, here is my x-axis, and here is my y-axis. And so the mg, the weight, is going to make an angle theta with the y-axis. That's the key thing that you have to recognize. So now we have this mg, which is pointing straight down, and of course it makes an angle with the y-axis, so we have to break everything down into x and y components. That's our procedure. We draw our vector arrows on the system, we put a coordinate system, and then we break all the vectors into x and y components. So mg is going to have a y component, which I'll just call mgy, and then it's going to have a x component, which is again parallel to the x-axis. I've drawn it tail to tip twice style here so that you can see the triangle. And here theta is now the opposite angle of the x component and the adjacent angle of the y component. That's completely backwards from what it normally is. We've done a lot of problems where the x goes with the cosine and the y goes with the sine, but here that's reversed, because the y is the adjacent side and the x is the opposite side. So this mgy, if mg is the hypotenuse here, and it is, then mgy is going to be mg times the cosine of the angle theta. and mgx, which is the opposite side of the triangle, and mg is the hypotenuse again, the opposite over the hypotenuse is the sine, so mgx is going to be mg sine of theta. So I have it written over here, the x component of mg is mg sine of theta, the y component of mg is mg cosine of theta. Now, what does any of this mean physically? This mgy, that is the component of the weight, the component of the force of gravity that's pushing the block into the plane. That's why the block doesn't leap off the inclined plane, because gravity is holding it into the plane. This is the part of gravity pushing the block against the inclined plane. Now this part, the x component of the weight, that's the part of the weight that's making it slide down the plane. And so gravity is doing both of these things. It's holding it against the plane and it's making it slide down the plane. Now, of course, since gravity is causing the block to be pushed into the plane is going to push back in the opposite direction with the normal force. And again, that normal force, normal means perpendicular. Perpendicular to what? Perpendicular to the inclined plane. So we have the normal force, we have the component of gravity that's along the y-axis opposite the normal force, and we have the component of gravity, the component of the weight, that's parallel to the inclined plane, and that's the part that's going to make it slide down the plane. So now we can apply our Newton's second law in the y direction and the x direction. Just as a general rule, I like to always do the y directions first. It doesn't matter. You can do them in any order you like, but I usually will do the y first just out of habit. And so here I've got the sum of the forces in the y direction, and there's two forces in the y direction. Remember, my y direction is pointing like this, my x direction is pointing like that, down the plane and perpendicular to the plane. So the two components, the two forces along the y-axis are the normal force, which is right here, and the y component of the weight. And so we can sum the forces in the y direction. It's the normal force minus mg cosine of theta. And remember, this is just mg y component. And so that's what we plugged in there. And of course, the acceleration in the a direction is 0. Why is it 0? Because it's not leaping off the plane. There's no motion in the y direction. In fact, that's why we tilted our coordinate system in the first place. That prevents any motion in the y direction, so all of the actual motion is going to be along the x-axis, which makes our life a little bit easier mathematically. Using this, so we've got the Fn minus mg cosine of theta equals to 0. We can solve for the normal force, and that works out to be mg times the cosine of theta. And again, the normal force is what's balancing the part of the weight that's pushing the block into the plane. Now we can do the sum of the forces in the x direction, and that's going to be the sum of the forces in the x direction. There was only one. There was mg times the sine of theta, mg sine of theta. And that was the component of the weight that was parallel to the inclined plane. Now, of course, we also had the other component, mg cosine of theta, which was perpendicular to the plane, and we had the normal force in the opposite direction. And of course, if I take the two gravity components, mg is going to point straight down. We'll pretend that I drew that straight down, but you guys get the idea. But in the x direction, the only force is mg sine of theta, and we can see that the way I've set up my coordinate system, it's going to be positive. And so the sum of the forces in the x direction are just mg sine of theta, and that's equal to ma sub x. So that's what I have here, the sum of the forces in the x direction, mg sine of theta, it's the only one, equals max. And of course, I can see that my masses are going to cancel out. I can divide both sides by m, and I get my answer here that the acceleration in the x direction is g times the sine of theta. And so that should work for any theta. Now, here's the interesting thing. We can actually test this. one of the things that physicists like to do, if you have a theory that gives you some general answer, like, so this is the acceleration in the x direction for any angle theta that you plug in. So any angle that you incline this plane, you can tell me what the acceleration is. We can plug in some values of theta for which we know what the answer should be and see if this answer gives us the right value. When you do that, you call that testing a limiting case. So we have two limiting cases for theta that we can test. We're going to test theta equals to 0, and we're going to test theta equals to 90 degrees. And so what does that mean? It means I'm going to plug these values of theta into my expression and see if I get an answer that makes sense. So when theta equals to 0, that means the inclined plane is flat. It has no angle. And so the acceleration in the x direction, and remember, my x-axis is going to be pointing like this, my y-axis is going to be pointing like that, and of course if I tilt the angle up, then the x and y-axis tilt with it. But the acceleration is going to be g times the sine of 0, and if you plug 0 into your calculator and hit sine, or if you happen to remember that the sine of 0 is 0, you'll get that the acceleration in the x direction is 0. Does that make sense? I hope it does, because if you have a block sitting on a flat surface, gravity is not going to make it accelerate to the left or the right. So there's no acceleration in the x direction if theta is 0. Our limiting case makes sense. What about the other one? If I have my inclined angle at 90 degrees, so it's a right angle, and again, my xy is going to point like this. So this will be my x-axis, and this will be my y-axis. When you plug in 90 degrees for theta, you get a sub x is g times the sine of theta, which is the sine of 90 degrees. The sine of 90 degrees is 1. And so you get the acceleration is g. Now remember, we're not having any friction in this case, so this is equivalent to something sliding down with no friction in the vertical direction. It's equivalent to something just falling. And that would be a case of something that we know should have an acceleration of little g. And so, again, our limiting case makes sense. It's what we predict it should be. And that's always nice to see.